Hello, my name is Weston Simmons. My teammates and I are going to show you how we modeled the SIMIODE competition's Problem B, throw the bike or throw the race. When we first began to contemplate this problem, what came to our minds was what is the net force of the cyclist before they perform the bike throw? And what assumptions do we need to incorporate into our system of differential equations in order to allow us to better understand the problem that we're analyzing? So here are the assumptions that we incorporated into our model. The first one was we would have no headwind and tailwind. The cyclist would be on a flat surface, and the rolling friction would be negligible because it's such a short period of time when the cyclist actually performs the bike throw. And we would also have the internal bike system be 100% efficient. Then we would have the density of the fluid be constant. Now the fluid in this case is the atmosphere that the cyclist is in. Then we would have the standard pressure and the temperature of that atmosphere be constant. The force to the pedaling would be constant, and also, and lastly, all the movement would be horizontal. So this is our system of equations. As you can see, the constants are C, which is the bicycle's drag coefficient. Then we have rho, which is the density of fluid, which is the atmosphere. Then we have A, the characteristics of the frontal area of the bicycle. And then we have B, the bicycle's internal friction, which we made equal to 0 because in this case, it's in such a short period of time it becomes negligible. The same thing with R, the rolling friction. Short period of time makes it negligible. Then we have M, which is the mass in kilograms of the cyclist and the bicycle itself. Then we have the power that the cyclist is outputting, which is 2,400 watts. And then we had our initial conditions. Now this is the beginning of our thought process. We wanted our cyclist to be 150 meters from the finishing line when they begin to start even thinking about doing their bike throw. And we want the velocity to be 14 meters per second. Now, this is our system of equations with the bike throw. It's pretty much the same except with a few key differences. As you can see, our constants have been added. Now, we have the throw equal to 0.18 meters, and we have T of T, which is the time of when you do the bike throw. As you can see, our initial conditions have now totally changed.
Our approach to creating the model was to create a second-order differential equation and then try to create a systems of linear equations out of that. And we just started out with force equals mass times acceleration, and then some algebra will give you acceleration equals force divided by mass. To get our equation for acceleration, we considered all the forces acting on the bike and the rider, and to the right on the slide is our free body diagram that shows all the forces. Putting together all the net forces and then doing some algebra, we get the second order differential equation of someone not throwing. As a result, we get our two equations, one for the throw, one for the non-throw. The only difference is the fact that the differential equation for the throw does not have the power term because they stop pedaling when they throw the bike, and so power goes to 0. To turn it into a system of linear equations, what we do is first we just enter in the formula for drag, which ends up having velocity squared in it, and then we let dx dt equal v, and then dv dt equal the formula for acceleration. Unfortunately, it is nonlinear, so we end up having to solve it numerically. To solve it, we used a program called R. We just input it in there and then used commands to solve it to get our position of the bike and rider at time t, we end up getting a graph that looks like this. And there are two lines on the graph. One of them is the person just pedaling through the finish line. The other one is when the person throws before they hit the finish line. And we have the finish line as being x equals 0. So whichever line crosses that first is the one that wins.
So for our results revealed that the best time to do the bike throw, given our initial conditions, is any time between roughly 10 meters from the finish line and the finish line itself. This will be a time interval of roughly half a second and result in a finish a few thousandths of a second or perhaps 1/100th of a second faster. If you throw before then, you will finish slower. And then obviously if you throw after the finish line, you're not going to finish any faster at all. So as you can see from the graph, if you do the throw about 14 meters from the finish line, or 7.4 seconds after the start of the sprint, you will do the throw essentially too early and finish after the time as though you did not throw at all. Then as you can see on this next graph, if you do the throw about 10 meters from the finish line or 7.6 seconds after the start of the sprint, you will finish roughly at the same time and not gain any time on your finish. Then we can see from the last graph that if you throw about 5.8 meters from the finish line or 7.8 seconds after the start of the sprint, you should finish faster than if you didn't throw at all. So following our results, we tried to figure out how we might improve the model, and we thought of developing powers of function, modeling a hilly finish, and modeling a non-discrete throw. So for powers of function, instead of using a constant for power in part of our equation, we could develop an analytic or symbolic representation of a power function, or ideally, if we could get it working with the R, have inputs of some discrete graph of maybe experimental data or something. Another improvement could be incorporating force due to gravity down the hill, modeling a hilly finish by either some simple method as a triangular hill, or ideally having a graph that represents the hill's horizontal and vertical positions, then using a derivative to find the angle of the hill at any given position, then using that to determine the force due to gravity down the hill. One of our major assumptions was that the bike throw is a discrete event. Very obviously it's not, and on this time scale I think it would be important, if we were going for a more accurate model, to more accurately model how the position of the front of the wheel of the bike changes in relation to the center of mass of both the bike and the human system. But that would require more reading on how to separate those sections of free body interaction and then incorporate that into the model. And here's the list of references we used.